This is lesson 8.7, solving exponential functions. We're going to start with a quick bell ringer. So if you're on your own, you should try these problems and pause the movie or video and then restart to check your answer. Okay, assuming you've attempted these already, we'll go through how to do them quickly. What is log base 2 of 8? We can use the exponential form to help solve this. So change this to 2 to the x equals 8. When we look at this, we know that if x equals 3, we get 8. So what is log base 2 of 8? It is 3. So logarithmic functions give us an exponent here. Okay, in 12, whenever x is greater than 0, log base 3 of 27x to the third equals. Here what you want to do is separate using properties of logs. So we've got log base 3 of 27 plus log base 3 of x to the third. And this is a 3. Okay, so I was able to split that into addition because we know we've got 27 times x cubed. And when you have multiplication inside a logarithm, you can split it into two separate logs that are added. So now we can think about evaluating this. Log base 3 of 27, so we want to think about 3 to what power equals 27? Well, if x is 3, you get 27. So this becomes 3 plus properties of exponents. We know we can move this exponent 3 down to the front. So this becomes log of 3 times log of base 3 of x. And that means that our final answer is J. Okay, so on to new material. Before we start going over some new problems, how to solve exponential equations, we should quickly review some important properties. There are two basic ways to solve an exponential equation. One relies on one-to-one properties, which you've listed here, one-to-one properties, and the other uses inverse properties. So one-to-one properties are here, and it's like this. If log base a of x equals log base a of y, then x must equal y, right? If these two things are equivalent, they're both logarithms to the same base, x has to equal y. Similarly, if you have a to the x equals a to the y, then x must equal y. So that's one-to-one. It's when these two sides look the same, the variables must be the same. Inverses are operations that undo each other. So addition and subtraction are inverses, multiplication and division are inverses, etc. Logarithms and exponential functions are inverses. They undo each other. So here if you have log base a of a to the x, this log base a of a is going to cancel out, leaving you only with x. Let me clear this up. So it's like this log base a of a cancels, leaving you just with that x. Here, if you have a to the log base a of x, the a and the log a cancel, leaving you with x. So we're going to use these inverse properties to help us solve exponential functions. So let's take a look at some examples. We're going to start simple using one-to-one properties. If you have 2 to the x equals 32, we're thinking about what exponent here would change 2 into 32. We could do that mentally, or you could rewrite the right-hand side so that you have 2 to the x equals 2 to the 5th. So we know 32 is equivalent to 2 to the 5th. So I've changed this so that they're both base 2. Then, using one-to-one properties, we can say, well, x must equal 5. So if the two sides are equal, they have the same base. The exponents must be equal. Okay, B, 2 to the x minus 5 equals 27. This is a really similar problem, but we have this negative 5 out here. We have to move that so that you've got your base and exponent alone. So the goal is to isolate 2 to the x. In order to do that, we add 5 to both sides, so plus 5, plus 5. We get 2 to the x equals 32. And then this becomes the same problem we had above, where we find that x equals 5. Okay, So that is a way to solve using one-to-one properties, but there are lots of problems where you cannot use one-to-one properties. And we've got some examples here. 4 to the x equals 11. There isn't any whole number exponent that can change 4 into 11. So we have to find a different way to solve these. We're going to do that using the inverse properties. So if we're trying to solve for x, we need to get rid of this 4 somehow. A common mistake is to divide by 4, but that does not work. You can't get rid of a base 4 to the x. You can't get rid of the 4 by dividing. Instead, you have to take a logarithm. A log is the opposite or inverse of an exponential function. So we have to do log base 4 of 4 to the x equals log base 4 of 11. So notice I chose log base 4 because our base was 4 here and we're trying to get rid of this 4. And what I do to one side I have to do to the other. So you see log base 4 on both sides. So what I'm doing here is I'm using, oops, it's on the previous page. I'm using this property, this inverse, where if you take a log base a of a, the log and the a cancel, leaving you only with the exponent of x. So here in 2a, we've got log base 4 of 4. Because these are inverses, this cancels, leaving you only with x. So you have x equals log base 4 of 11. Okay, now if you have a calculator, you can plug this in and get an answer. I'll post some brief notes and a quick video on how you translate this. Depending on your calculator, you may be able to use the math function. So on your calculator, there's a math button. Oops. It's a little messy, math. And then on mine, I scroll all the way down to A, and it says log base. And when I click on that, it gives me this log and then an empty spot for the base, and then what I'm taking the log of. So when I plug in log base 4 of 11, it gives me 1.7297 with some additional numbers afterwards. Now, in pre-calc, we usually round to 3 decimal places. If I was going to round this to 3 decimal places, it would be 1.7. This 7 pushes the 9 up, and this 29 becomes a 3, 0. So 2a, the answer is approximately 1.730. Okay, now let's take a look at b. E to the 4x equals 7. Well, what is the inverse of e to some base? The log that corresponds to e is the natural log, or ln. So we're going to take the natural log of both sides, so ln of e to the 4x equals ln of 7. ln and e cancel because they're inverses, leaving us with 4x equals the natural log of 7. Now, I can either divide both sides by 4 and get the natural log of 7, divide by 4, or you could multiply both sides by 1/4 and get 1/4 times the natural log of 7. Either of these is correct. I generally prefer this version. Some students prefer this one. And then I would plug this into my calculator and round to 3 decimals. When I do that, I get approximately, I'm running out of space here, 0.486. And when I plug this into the calculator, I don't need to go to the math function or button. There is a button for ln. That's the one that you want to use on your calculator. It's right below the log button. Okay, so now you have some practice problems where you can try this on your own. So I'd suggest pausing the video, trying it on your own, and then checking your work again, or against mine, in a minute. Okay, so here are the answers that you should have gotten. On number 1, we take log base 8 of both sides. Log base 8 of 8 cancels, leaving you only with x. And then on the right-hand side, you have log base 8 of 20. So we would say that this is the exact answer. because the instructions ask us to find both the exact value and then an answer rounded to the nearest thousandth. So that's 3 decimal places. So this is the approximate, I'll put approximate answer, right, rounded to 3 decimals. In number 2, you take the natural log of both sides because we have an e. You get negative x equals the natural log of 5, divide both sides by negative 1, or multiply both sides by negative 1, and you get negative natural log of 5. Plug that into your calculator, you get negative 1.609. So exact answer and approximate answer. In 3, because you have base 7 here, you are going to take log base 7 of both sides. Log base 7 of 7 cancels, leaving you with 3x equals log base 7 of 18. Then you can either divide by 3 on both sides or multiply by 1/3. I multiplied by 1/3, so I have x equals 1/3 log base 7 of 18, and you plug that into your calculator and you get 0.495. Okay, let's take it a step up where there are a couple more steps in the problem solving process. So again, we want to isolate the base, and then we're taking the logarithm of both sides. So in this example, we want to isolate 5 to the x. In order to isolate 5 to the x, we are going to add 2 to both sides. So we get 5 to the x equals 49. Now I want to get x alone, and the way I get x alone is by taking log base 5 of 5 to the x. And you take log base 5 of both sides. Okay, so now log base 5 of 5, this is going to cancel, leaving us just with x. So I get x equals log base 5 of 49. And if you plug that into your calculator, again, you would go to math. I'm going to option A. You might have a different option. And then put in log base 5 of 49, and we get approximately 2.418. We're going to use both of these as answers, an exact answer and an approximate answer. Okay, looking at example D, we still want to isolate our base and exponent. So in this case, what we're trying to isolate is 2 to the 3x plus 3. So first I want to get rid of the 5 so I can isolate what's in the parentheses. I do that by dividing because the 5 is being multiplied to this set of parentheses here. So when I divide, these 5's cancel, and I get 2 to the 3x plus 3 equals 10. Now I want to get rid of this base 2. I can't divide, I have to take the logarithm of both sides. So I get log base 2 of 2 to the 3x plus 3. And you take log base 2 of both sides. And I get log base 2 of 2 canceling. So that leaves me with, let me go up here, 3x plus 3 equals log base 2 of 10. Now don't change log base 2 of 10 into a decimal until the very, very end. We leave it exact. So here to get x alone, I'm going to subtract 3. And I get 3x equals log base 2 of 10 minus 3. I can't combine this minus 3 with anything in the logarithm. This is like a closed function. I can't take 3 away from 10 because the 10 is inside the logarithm. So my final step to get x alone, I'm going to multiply both sides by 1/3. So I get x equals 1/3 parentheses log base 2 of 10 minus 3. And then I'm actually going to cross this out and give us a little more space to work. I'm going to distribute the 1/3. So I get 1/3 log base 2 of 10 minus, and I'm distributing this 1/3 both to the logarithm and to the negative 3. What's 1/3 times negative 3? It is 1. So I get a minus 1 here. So 1/3 log base 2 of 10 minus 1 is an exact answer. Then I'm going to plug that into my calculator. And I'm going to get, let's see, log base 2 of 10 minus 1. Okay, 0.107. So this is the exact answer and the approximate answer. Okay, so now you've got 2 practice problems. Pause the video, try these on your own, and then start up the video again and check your work. Okay, so here we have the answer for number 4. I divided both sides by 4. Then I got e to the negative 2x equals 17 over 4, or you could have changed it to a decimal. Then we need to get rid of the e, so do the natural log of e to the negative 2x, natural log of 17 over 4. The ln and the e cancel out over here, and then we have negative 2x equals natural log of 17 over 4. To get rid of this negative 2, I multiplied both sides by negative 1/2, and I got x equals negative 1/2, natural log of 17 over 4. Plug that into the calculator, you get approximately negative 0.723. Okay, for number 5, we start by subtracting 16 from both sides. After that, you divide by negative 3. You get e to the 2x equals 11 over 3. Do not change 11 over 3 into a decimal. Leave it as a fraction because it's exact. Then you take the natural log of both sides, and you get here 2x equals the natural log of 3 over 2. To get rid of the 2, I divided both sides by 2 or multiplied by 1/2. And you get x equals 1/2 natural log of 11 over 3. And as a decimal, careful when you round here, a lot of people will make a mistake. The decimal is 0.6496. This 6 pushes the 9 up to a 10, which means this becomes a 0, and this becomes a 5. And this disappears. So 0.650. Okay, let's take a look at 6. Okay, in number 6, the goal is still to isolate the variable. So we have to start by getting 6 to the negative 4x plus 1 alone. I do that by multiplying by 3 to both sides. That gets rid of the 1/3 over here. I multiply 3 to both sides, so on the right-hand side I get 3 times 6, which is 18. So now, because the 3 and the 1/3 cancel, I've got 6 to the negative 4x plus 1 equals 18. Now I want to get rid of the base 6. I do that by doing log base 6 of 6 to the negative 4x plus 1, and what I do to one side I have to do to the other. So I get that equal to log base 6 of 18. The log base 6 of 6 cancels here, leaving us with negative 4x plus 1. Subtract 1 from both sides. You get negative 4x equals log base 6 of 18 minus 1. Remember, you cannot combine these. The minus 1 is on the outside of the log. The 18 is inside the log. So leave these separate. Then to get rid of this negative 4, I multiply both sides by negative 1/4, giving me x equals negative 1/4 log base 6 of 18 minus 1/4. So you have to distribute that negative 1/4 both to the logarithm and to the 1, which makes this a negative 1/4. When you plug that in the calculator, you get approximately negative 0.653. Okay, you are now ready to try the homework. If you have any questions, let me know.